Okay, it's a pleasure to be here. We've just had two um, 2 days of meetings of the advisory committee of the IIP, which have been very interesting, and in the end, I think very optimistic. I look forward to the continuing success and future of this institute, and it's in excellent hands. And although Institute has gone through and is going through a difficult period, it certainly isn't their fault. And brighter days will come soon. So I'm going to, this year is the 50th anniversary of quantum chromodynamics, the theory of the strong interactions. And this talk will be devoted to discussing the history that led to this theory, the present status of the theory, and some open problems, and the perspective of history, if you want. 50 years is a long time, and I'm sure most of the audiences I can see were not alive 50 years ago. And I suspect that for many of you, your parents weren't alive 50 years ago, which is very sobering, I must say. And it's always fun to look back. If we go back another 50 years, we are not working. Why did this suddenly go wrong? It worked a moment ago. Okay. While he fixes it, I will go on. If we go back another 50 years, we're nearing another even more momentous anniversary, 100 years of quantum mechanics. It's roughly next year 50 years old in the form it still remains the theory of the world. And if we go back, well, and here we are now. Now I'm going to start my story even farther back with the discovery of the nucleus, which is now 110 years ago. A momentous experiment by Ernst Rutherford, who discovered the nucleus of atoms in 1911. Now, the experiment that Rutherford carried out in 1911, in my opinion, is the most momentous experimental discovery of the 20th century. Rutherford discovered not just the nucleus of atoms, but the structure of the atom, which led quite rapidly to quantum mechanics, and he invented the experimental tool that we still use today to explore the fundamental structure of matter. 3 momentous discoveries, 3 Nobel Prize winning achievements. Rutherford never won a Nobel Prize in physics. He should have won 3, but he died rather young. What he did was decided to try to figure out what the atom was made out of by shooting particles at the atom. And what he shot were alpha nuclei, alpha particles, which he had discovered or used in his studies of radioactivity. So radioactive nuclei produced alpha particles, which he could collimate, create a beam of alpha particles, and he shot them into a gold screen. And his detector were Marsden and Geiger, a postdoc and an undergraduate, who sat for hours in a dark room until their eyes were sensitive enough to detect the scintillations that the deflected alpha particles made on this screen. And they measured the angles at which the various alpha particles were deflected from the nuclei, from the atoms. And to his surprise, there were many events where the deflected alpha particles were deflected at large angles or came back directly towards him. He famously said, "This is like throwing a brick at a piece of tissue paper and the brick comes back at you." Nobody expected that. The atom was thought to be a diffuse structure, and with most of the alpha particles should have just been deflected a little and passed through. He concluded alpha particles are positively charged nuclei, and the fact that they came back due to the force of electricity, the force between the alpha particles and the wherever the positive charge of the atom was localized, that it had to be the case that most of the mass, 99% of the mass, and all of the positive charge of the atom was localized in a very small region, 100,000 times smaller than the radius of the atom. It was so small he couldn't even measure it. He could just put an upper bound. And that was the discovery of the nucleus of atoms. It took quite a while to make further progress, another 20 years before the other constituent of nuclei was discovered, the neutron, by Chadwick, 1932. But that started the existence of the nucleus as a subject of scientific investigation. More importantly, at least immediately, was that this gave rise to an obvious model of what the atom was. You have the sun, planets revolving around the sun. You have the nucleus and electrons revolving around the nucleus. That classical model of the atom, the Rutherford's model, was obviously wrong, since electrons would radiate as they accelerated around the nucleus, and the atom would be unstable and decay, disappear immediately. 2 years later, Bohr introduced quantum mechanics into the game and stabilized the atom, constructed the Bohr model, extraordinarily successful in describing the spectrum, the measured spectrum of hydrogen, and within almost immediately an idea of the periodic table and the structure of all atoms and then molecules. Bohr's model of the atom was clearly wrong. It couldn't be generalized. But 10 years later, with centenary we will be celebrating next year, quantum mechanics in the form we now know it was developed, driven by the necessity of explaining the Bohr model, which was based on the Rutherford model, which was based on the discovery of the nucleus. Very little extra experimental information was required to go from the Bohr model to quantum mechanics. So those are two major accomplishments of this experiment. And the third being that the method that Rutherford used is the one we still use today, albeit with much more complicated and energetic creators of energetic protons, which we shoot now at other energetic protons to increase the energy. That's what we've been using for 110 years to probe the structure of matter and nature at shorter and shorter distances. We have not conceptually improved on Rutherford's method. We might have to, because this is beginning to be too expensive and too difficult. And instead of Rutherford's the use of Marsden and Geiger, we now have very complex, unbelievably intricate, beautiful, precise detectors. This is a picture of the Atlas detector at the LHC at CERN. Well, when I was a graduate student, I was a student at Berkeley, which was the center of high energy physics experimentally. It had the biggest accelerator in the world for some number of years. 6 billion electron volt energy, which is 1,000 times less energy than the L8C today. But the same idea. In that case, you smashed protons on a fixed target, lots of particles were being produced, and you hope to explore the structure of the proton, the neutron of nuclei. Now, it was clear to me that, and to everyone actually, that this strong force that held the nuclei together, the interactions which had something to do with what the proton is and how it interacts, was the most pressing problem and the most difficult problem. And that was especially intractable, but especially challenging. And so that's what drew me to be interested in the strong interactions. But the theoretical situation was really very primitive. What were the elementary particles? What was matter nuclei made out of? Which particles were elementary? At Berkeley, every few weeks a new particle was discovered. And as far as you could tell, these new particles, mesons and baryons, look very much like the proton or the pion. They all looked the same. It wasn't at all clear which were the elementary particles and which were the composite particles. And even if you could identify the elementary particles, and in the beginning, since they were originally found, the elementary particles were thought to be the proton, the neutron, and a carrier of force. The carrier of force was hypothesized by Yukawa to be originally a vector, then a scalar particle, and it was shortly discovered in cosmic rays. So you had a kind of something like the photon, which mediates electromagnetic interactions. You could try to construct a theory based on protons, neutrons, and pions, whose exchange gave rise to the nuclear force. But even if you identified correctly the elementary particles, and once you were producing dozens of such particles, it wasn't at all clear which you start with, you couldn't calculate because the force is very strong. And physicists are very, they're pretty good at calculating by perturbing around something that is trivial. So if you have a weak coupling like electrodynamics, you start with free theory, you add a weak interaction, you can calculate quantum corrections in a perturbative series in 1/137. But the same quantity in the case of the strong interactions, say the coupling of the pion to nucleons, was very big. You couldn't perturb in it. So nobody knew how to calculate, even if you knew which particles to start with and what dynamics to suggest. Freeman Dyson, who contributed very importantly to the development of quantum electrodynamics, the quantization of Maxwell's theory, which was very successful, tried very hard for a few years to take mesons, pions, neutron, proton, and construct a similar theory of the strong interactions. And he failed miserably. And he gave up. And typically when physicists give up, they conclude the problem is impossible. That's why they couldn't find a solution. And Dyson famously remarked, the correct theory will not be found in the next 100 years. He was off by 87 years, but that was the feeling at the time. And the general feeling of physicists who, in fundamental physics, who discover an impossible problem, think, okay, we need a new revolution. And after quantum mechanics, a lot of physicists believe whenever they encounter a problem, they need another revolution like quantum mechanics. The deep reason why it was so hard to understand the strong interactions from today's point of view is that the charges that source the fields that provide the forces, which we now know are quarks and gluon, which carry a charge much like the electric charge, except now there are three of them, three colors we call them. That's why it's quantum chromodynamics. The charges, which and the elementary particles that carry these charges that source the fields and from which the other particles are constructed, are hidden. They're invisible. No matter how hard you smashed particles together in these collisions and you looked at what comes out, you never saw the quarks that we now know are the fundamental elementary constituents of hadrons, of heavy nuclear matter. When you smash atoms together, out come electrons. You make them run in wires, you create the Industrial Revolution, but you can't do that with quarks. Quarks can never get out of the nuclei. Actually, it took a while till people even proposed that, well, something elementary about fractionally charged objects called quarks inside the proton, but they really were regarded as mathematical tricks to summarize patterns of symmetry that were discovered in the families of particles that were being produced and not taken seriously because you should produce them. But the even more serious problem was that the conceptual framework of fundamental physics at the time was quantum field theory. That was the basis for the very successful theory of quantum electrodynamics. You have a field theory like Maxwell's electrodynamics, you simply quantize it. That was technically difficult and it took too long, but it was a technical problem. However, by this time, people were very unhappy and suspicious of quantum field theory for a variety of reasons. One reason was renormalization theory, which was developed to try to get rid of the ultraviolet infinities that occurred in perturbative expansions, the quantum corrections to quantum electrodynamics. And renormalization was proposed by Feynman, Schwinger, and Tominaga, and Dyson, and it was very successful in enabling people to express physical observables like G minus 2, the magnetic moment of the electron, in terms of physical quantities like the fine structure constant, 1 over 137. But it was thought to be a trick. This was some kind of trick that people used to get rid of infinity, sweep them under the rug. It's fishy. There's probably a revolutionary new theory which makes things finite from the beginning. The inventors of quantum field theory, Dirac, Heisenberg, and their colleagues, never believed in quantum field theory, and within a few years suspected that a revolution was necessary. Second, even if you accepted renormalization theory, you couldn't calculate. There were no non-perturbative methods available. The first course I took in quantum field theory was with Steven Weinberg, a great theoretical physicist, and one of the architects of the Standard Model. And the first thing he did in the course was write on the blackboard field theory equals Feynman diagrams. That was it. Feynman diagrams are the perturbative expansion of observable quantities in quantum field theory. And if you have strong coupling, this perturbation theory is useless. Now, there was a successful quantum field theory of the weak interactions. Inside the nucleus, we now know, and it was already understood, that there were two kinds of forces. One was a strong nuclear force that held the nuclei together. The other was whatever force, whatever theory there was that explained radioactivity, the instability of nuclei to emit beta, alpha, beta, gamma radiation. And that was a very weak force at the low energies that were being explored. And Fermi wrote down in the 30s already what we would today call an effective field theory, a phenomenological theory of the weak interactions, where the Hamiltonian was a quartic in the nucleon field, and then the proton field, the neutron field, the electron field, the neutrino field. He had to invent a neutrino to make this work. And but that was a phenomenological theory. It was not renormalizable. You couldn't get rid of the infinities. You couldn't make it unitary. And that was okay because one was working at low energies at that point. And so you could use this theory at least to describe what was observed. The theory that turned out to be crucial for the rest of the standard model, especially the strong interactions, is Yang-Mills theory, which is a non-abelian version of Maxwell's theory, in which there's more than one kind of charge. But again, there's a local symmetry underlying that theory, a gauge symmetry, except that since there are multiple charges, the gauge fields are matrices, or have two colors, color, anticolor. They connect colored quarks to the anticolor particles of colored quarks. And they themselves, therefore, are charged. So the theory is quite complicated, but it's like all gauge theories, at least at the classical level, plagued with massless particles. In the case of Maxwell, the massless particles were the quanta of light. I always think one of the greatest moments in science history is when Maxwell calculated the speed of radiation, and his theory discovered that it was within errors the same as the measured speed of light. But in our case, non-abelian or gauge theory, Yang-Mills theory, these massless particles are never seen. So that held back the application of Yang-Mills theory for a decade or more. Although people did try to apply this idea of a theory which was had a principle for the dynamics, that of a non-abelian version of Maxwell's gauge symmetry, to the strong interactions, and they coupled the gauge bosons to a partially, almost conserved current or charge flavor. Quarks come in different flavors. We say up quarks, down quarks, charm quarks, strange quarks, top quarks, bottom. There are 3 kinds of flavors, 6. And the light ones are almost very light and almost the same mass. So maybe there's a symmetry, and that is what they tried, but it's not really a symmetry. These charges are not really conserved, and it makes no sense mathematically or physically to couple basic gauge theory on non-conserved charges. So it didn't work. And then there were two serious conceptual attacks on the whole structure, namely on quantum field theory, as the basis for relativistic quantum mechanics. The first attack was prevalent at Berkeley in the West Coast, where I was a student. In fact, my thesis advisor was the great prophet of this attack. And it was based on two ideas. One is there were all these particles, literally dozens of proton-like particles, hadrons. They all seemed equally fundamental, structuralist, or at least fundamental. So what Chu said, well, instead of trying to construct a theory where you have a bunch of elementary constituents and then you make everything else out of them, everything else is some kind of composite of the elementary constituents, you say all hadrons, and there might be an infinite number even, who knows, we're discovering more every week, they're all equally fundamental. And you might say that particle C is made out of particle A and B, or particle B is made out of A and C. Okay, interesting idea, very democratic, but how do you construct a theory like that? Second idea, which has now come back into vogue, is something called the bootstrap theory, which is even more radical. There is no theory, in a sense. There is no Hamiltonian that describes the interaction. There is no Lagrangian whose least action gives you the equations of motion. But there are general principles that we all accept, like causality, cause precedes effect, and that in relativistic quantum mechanics leads to analytic properties of the observable scattering amplitudes. And the other principle is unitarity, namely, quantum mechanics, we calculate probability amplitudes whose square gives us the probability for observable events or outcomes of experiments. And you better make sure that if you calculate the probabilities, they add up to 1. Something is going to happen. You don't want negative probabilities, that's meaningless. You don't want probabilities to be less than 1. Then what happens? And so on. That's an important constraint on observables. In fact, it's very difficult, and at the time it was almost unknown to find examples of consistent scattering amplitudes that were consistent with these general principles. Scattering amplitudes is what's observed in Rutherford-like experiments, which is sort of the only thing we know how to measure in relativistic quantum mechanics. You shoot particles together, particles come out, you can measure the probabilities that they come out different angles. That's what you calculate, that's what you observe. So it's so hard to find examples of relativistic quantum mechanical scattering amplitudes because in relativistic quantum mechanics, you always produce particles, except in special cases, integrable theories. So it's always a many-body problem. 2 particles produce 2 particles, but they also produce 2 particles plus 2, 4 particles. You can always create another particle and its antiparticle out of energy. And then 4 particles can produce 6. Never ends. And again, physicists say, okay, well, problem is so hard, there must be a unique solution. Now we know that's certainly not true. There are many, at least the innumerable infinite number of consistent S matrices. And, but that was the idea. All particles are fundamental. You write down the constraints on the observables, on the scattering amplitudes. satisfy these general principles, and nature will emerge as the unique S matrix that satisfies general principles. Now, across the ocean, the other side of the Iron Curtain, there was another attack on quantum field theory led by Lev Landau, the leader of the Landau School of Physics, immensely powerful school of condensed matter physics, particle physics, relativistic quantum mechanics. And this problem is called the problem of zero charge, or the Landau pole. What Landau and his collaborators did was, in the framework of quantum electrodynamics, today we would say they studied the high energy behavior. But the way they were looking at it was, you start with quantum electrodynamics, where to define the theory and deal with these infinities that occurred when you considered very short distances, you introduce some kind of cutoff, at very high energies or very short distances, at which you define the theory with what is called the Baire coupling. Now, quantum mechanical effects renormalize that coupling, and physically what you measure is the physical coupling. What they studied using the very simple first-order quantum effects was the relationship between the physical coupling you measure, the Baire coupling you put into the theory. And what they found in the simple approximation was that in all theories, and they didn't discuss many theories, but some, the physical coupling vanished no matter how big you made the Baire coupling. And something like this. The physical coupling was the Baire coupling divided by a power series, which could be resummed to give 1 plus e squared log lambda. This is the cutoff. And you're supposed to fix this coupling. This is what you measure. And then you have to, of course, take the cutoff away, go to the continuum limit. But no matter how big you make E naught, as lambda goes to infinity, EP vanishes. So that's the problem of zero charge. Now, the origin of this problem is very simple physically. It's screening, as we talked about screening yesterday. Itamar is waking up, he hears his name. And he talked about screening yesterday. If you put a charge into a medium, it's screened by dipoles. Now, in the vacuum, there are always dipoles because of quantum mechanics. You can virtually create pairs, electron-positron pairs, which are like little dipoles. And in the presence of the external charge, they will screen it. Now, in quantum field theory, that screening is the dielectric constant that is produced is distance dependent. And the electric force, which is reduced by the dielectric constant, gets bigger and bigger if you go to large distances. So the electric field, the force exerted by this external charge, decreases. Conversely, if you go to shorter distances, it increases. That is the phenomena that was summarized by that formula that I wrote down. And in fact, this is true for what we now call non-asymptotically free theories, where as you go to shorter and shorter distance, like in a dielectric medium, less screening, stronger force. And Landau kind of, I'm not sure I don't think he based this on the physical argument of screening, but just generalized what he could see from slowest order calculation. And he reached the conclusion that within the limits of formal electrodynamics, a point interaction, so a local interaction where you really try to define the theory by the coupling you see at arbitrarily short distances, for any intensity whatsoever is equivalent to no charge at all. We are driven, therefore, now Landau was a bold physicist always, so the fact that he was just concluding based on electrodynamics, treated perturbatively, in effect, he was driven to the conclusion that the Hamiltonian method, quantum field theory, for strong interactions is dead and must be buried, although, of course, with deserved honor. Why just strong interactions? This also happens for QED. The problem is that this is a problem of short distance behavior. The Landau pole, actually what happens is that if you go to shorter and shorter distances, the coupling gets stronger and stronger, and at some finite distance, it blows up, or finite, very large energy. In the case of electrodynamics, this energy where theory breaks down is so far from observation. It's much, much larger than the Planck mass or any energy scale you can imagine. You could ignore this problem being a practical person, and Landau was a practical person. But in the case of the strong interactions, where the coupling starts out big, to carry out such an extrapolation, you'd get nonsense very quickly. Now, Landau was a very strong personality, and he had strong enforcers, and he forbade his younger colleagues, my friends Migdal and Boyliko, for example, to work on quantum field theory. They were forbidden. They did so anyway. They claimed they were doing many-body theory, condensed matter physics. But it really was a strong and physically motivated attack on quantum field theory. So that was a theoretical situation when I was a student. Meanwhile, experiment was flourishing. Whole situation was exactly the opposite of today. Theorists were impotent, experimenters were enormously successful. They were finding new particles, new patterns of symmetry of these particles, proximate symmetries. It was a wonderful period. Now, the experiments they were doing were twofold. One was what they really, experimenters in high energy physics, particle physics, like to do, smashing particles together, looking at what comes out and seeing bumps which indicate new resonances, new unstable particles. But as far as dynamics, they believed, both theorists and experimenters, that the secret of the strong interaction lay in the high energy behavior of scattering amplitudes, that low momentum transfer. And when you scatter particles together, most of the stuff that comes out in the forward direction with very little deflection, just like the atom. And most of the experimenters were measuring things that the so-called forward scattering or diffraction scattering. And this was experimentally easy. Most of the events go in the forward direction. That's where most of the data is. If you're an experimenter, you want better statistics. There were also interesting patterns that theorists began to understand, Reggie behavior, Reggie poles. So there was this phenomena of experimenters and theorists confirming each other. Experimenters like this. Theorists found some patterns. They told the experimenters, this is really interesting, and so on. Very few people were interested in those rare events where the particles came back at you at large deflection, large momentum transfer, large angle. And that's where the secret of the strong interactions ultimately was found. Now, I escaped from Berkeley, went to Harvard, where quantum field theory was not as forbidden, and started doing what today would be called operator product expansions, except that that hadn't been invented yet. But trying to determine relations between observable quantities, not just scattering amplitudes, but matrix elements, hadronic matrix elements of currents, like the electromagnetic current, that could be probed not using protons, but using electrons that only interacted electromagnetically. That we understood. And one could use various hypotheses to explore what happened at short distances, and this could be related to these functions of momentum of the electrons and the proton that could be observed in electron-proton scattering. And we derived, for example, a sum rule, which is we now know is exact. We know the coefficient, which is in 1, which today in QCD we would say is a way of measuring the momentum energy content of the constituents of the proton, charge constituents of the proton. And Durkheim realized that the sum rule sort of suggested, dimensional analysis as well, that these cross-sections scale are only functions of ratios of momenta. And there are other sum rules that I derived. One of them, which turned out to be true, said that you scatter electrons off protons, you're essentially scattering virtual photons off. And the photon can be transversely polarized or longitudinally polarized. And the ratio of those cross-sections depended sensitively on the spin of the constituents. So we proposed this as a way to measure the spin of the constituents of protons. There were other sum rules which in effect measured the baryon number of the constituents. Anyway, I was primed for a new experiment, which began at SLAC when they constructed a electron-proton scattering experiment at very high energies for them, not by today's standards, large angles, where you could measure, do essentially what Rutherford was doing, using electrons to produce photons, which you could use to look inside the proton and see what it was made of. But just like, well, not just like, at that time, no one was interested in this experiment. No one said, or very few people said, well, this is what Rutherford did. It's going to be exciting. No, everybody assumed proton is this diffuse object. This is going to be just like Rutherford. Most of the events are going to be in the forward direction. Things are going to fall off exponentially. Just like the experiments at lower energies, you'll learn something about the distribution of charge within this diffuse proton. There were only a few experimenters who did the experiment and essentially, as it's now interpreted, discovered that the proton looked like it was made out of freely moving quarks. And for that, they were awarded the Nobel Prize for the discovery, experimental discovery of quarks. What they saw in this experiment could be interpreted as if you would say that the proton consisted of quarks that, when observed, were freely moving, like free particles. Therefore, you could easily calculate what went on. The quarks could be assumed to be massless. There was no scale. You got the scaling behavior. the sum rules that we had written down on the basis of just assuming that things were made out of quarks for no good reason, but why not? And we just used the totally unacceptable assumption that the quarks were free fields, because that's the only thing we could calculate, also worked. Now, it worked. Great experimental discoveries aren't always so clear. When you see a bump, that's pretty clear. When you see a process with errors of 20, 30% at energies which are kind of low, most people said, very interesting, but yeah, it'll go away, or didn't take it too seriously. But I did. And some people did. The experiments got better, but slowly. But if you took them seriously, as I did, partly because I'd been working on the subject and some of my sum rules worked, and there's nothing like experiments confirming you, or at least not saying it's wrong, that makes you believe in some speculations. Anyway, it convinced me that hadrons were made out of point-like constituents. Not only that, the charged constituents were quarks. If you assumed they were point-like and moving freely, then the sum rules really told you what their quantum numbers were, and they looked just like quarks. Fractional charge, fractional baryon number, spin 1/2, so on. But this is crazy. How could quarks be moving freely? You could then easily knock them out of the proton. So this was the confusion. Quarks must interact strongly, but if they interact strongly, how could you explain scaling or the sum rules? So I started studying scaling in quantum field theory, as did others. Scaling was a new idea in quantum field theory, because quantum field theory, like the world we see around us, has a scale, has masses. Masses violate scale invariance, set a scale. And the world is obviously not scale invariant. But it's an interesting symmetry to consider. But it was clear that even if you took a theory with no scale, quantum effects like that screening I talked about that depends on distance introduce a break scale variance. And the sum rules that we derive are clearly also destroyed by quantum effects. So this problem, how to reconcile, how could you have free point-like behavior, free at least at short distances, and you never produced quarks, obsessed me for about 5 years. Now, there was a detour into another theory being constructed just then of the strong interactions. That was string theory. A fascinating theory. But it was clear that in that form, of which we now call critical string theory, you cannot explain scaling. Instead of getting free field-like behavior, you would get very rapid exponential fall-off. Strings are very soft. Strings don't look like point particles, just the opposite. They look like soft, extended objects. So by 1972, I was ready to give up, or actually more ambitiously satisfy my thesis advisor and prove that quantum field theory was ruled out by experiment. And the plan was twofold. First was to prove that if you took the experimental results seriously, which most people didn't, that you had to have this phenomena of asymptotic freedom, which meant the opposite of screening. As you go to shorter and shorter distances, the coupling that characterizes the interaction goes to zero. Typically, it approaches a fixed point of the renormalization group, critical point. But in this case, it would have to be zero to explain asymptotic freedom you really get non-interacting particles. And Callan and I, 50 years ago, building on some initial work by Parisi, proved that for theories of spin 1/2, spin 0 particles, and QED, of course. Did not discuss Yang-Mills theory, where it turns out the proof fails. Then I was going to prove that asymptotically free theories don't exist. Now, how do you prove something doesn't exist? Not easy. But in the case of quantum field theories that we said made sense, by which we meant that they were renormalizable, by which one means that you could write them down and derive results with a finite number of parameters. That distinguishes renormalizable from non-renormalizable theories. There are only a countable infinity of such theories made out of spin 0 particles, spin 1/2 particles, and maybe spin 1 particles, although they have to be gauge theories. Intuitively, the idea is that of Landau, that I think was behind Landau's conclusion. Charge renormalization is vacuum polarization, essentially, is screening where the charge, and this is infinity, not 0, as you go to short distances. And Coleman and I eventually proved that any sensible field theory you write down, which has a ground state, is renormalizable. Any number of scalar particles or fermions or abelian gauge particles with arbitrary interactions can't be asymptotically free. And you can prove that because if you assume it was asymptotically free, then you could use perturbation theory to study that, because the coupling gets arbitrarily small if you go to short distances. Anyway, we proved that. The one theory that was not included here was more complicated, had just reappeared on the scene, non-abelian gauge theories, which were being used by Weinberg, Salam, Glashow, and Hoof to study, to improve on Fermi and derive a sensible unitary renormalizable theory of the weak interactions. So I'd worked on that, but non-abelian gauge theories were the one left to conclude this conclusion that if you took the experiments to mean that you really have scaling, you need asymptotic freedom, they don't exist, quantum field theory is dead. Okay, so my first graduate student appears, Frank Wilczek, said, why don't you work with me? We're going to close the gap. And instead, we did the calculation and discovered what we said. It's a remarkable fact, and to me, it was absolutely remarkable and surprising, that perhaps unique among non-renormalizable theories, this non-abelian gauge theories, non-abelian generalizations of Maxwell's theory, are asymptotically free, and asymptotically approach free field theory of short distances or high energies. And that could explain the scaling, which has so far eluded, and in fact, eludes all other possible quantum field theories. So for me, it was like, I once compared that to Moses, suddenly the burning bush speaks. Nature spoke and said, okay, you want asymptotic freedom? There's only one theory. Yeah, it has to be a Yang-Mills theory. And then it was clear what the theory was. There was really not much choice. And because we knew a lot in the 60 years preceding this about the nuclear force. The dynamics had to be non-abelian gauge theory. The quanta that held the quarks together had to be gluons. The matter had to be quarks because that's what you saw in the experiment. Quarks had three colors. We already knew that there were three kinds of degenerate quarks from a bunch of experimental measurements and very simple theoretical ideas like, so there was really no choice. And you couldn't add any other interactions because you would have destroyed asymptotic freedom. So one appealing model, we said in original letter, was that the three triplets of fermions, three because we knew about up, down, and strange quarks, with an SU3 color gauge group to provide the strong interactions. And that's QCD. Now, why does that happen? Why does QCD anti-screen as opposed to screening? And the best way to understand this is to think about, this is a relativistic quantum field theory, we're going to think about electricity or magnetism, they're just tools of each other. Let's think magnetically. What's new about non-abelian gauge theory is that the glue, the quanta of the force, is charged. Photons have no charge, okay? But gluons do. They are like dipoles. Well, not dipoles. They're permanent magnetic dipoles. Not pairs of particles, but this particle is a permanent dipole. It's the permanent magnet. And if you put a external magnet into a medium which contains virtual permanent magnets, they align. It's called paramagnetism. And now, if you go to larger distances, you have more anti-screening, more magnets, larger force at large distances, weaker force at short distances, just the opposite of a dielectric medium. Why Landau didn't realize that his problem was caused by diamagnetism. And all you have to do is think about paramagnetism. Maybe you could, anyway, he didn't think that way. But that's the reason. Now, in the longer version of the letter, we tried to, start calculating. Of course, new physics, you immediately calculate, make predictions. But in addition, we were very worried about, where are the quarks? Why don't we see the quarks? But asymptotic freedom also meant that the force did not decrease at large distances. In fact, it increased. The charge increased. And so there's no reason to believe that you could produce quarks. That becomes a strong coupling problem. And we conjectured that the infrared behavior, the behavior at large distances, could suppress all but color singlet states. The quarks are simply strongly bound. And that the colored gauge fields, the gluons that nobody sees, as well as the quarks, are never produced as asymptotic states. Now, this is sometimes called infrared slavery as opposed to asymptotic freedom or confinement. Now, this is true, we believe, not been proved, $1 million if you prove it, and is a simple consequence of Gauss's law and the dynamics of the vacuum. So, we use Gauss's law to derive Coulomb's law. You integrate the electric field over a sphere of radius r, E times the area of the sphere is the charge, that's Gauss's law. So you get Coulomb's law. And if you calculate the energy it takes to move the charges apart, it saturates at the ionization energy. That's all you need to ionize an atom. Finite amount of energy, you can kick the electrons out of the atom. But in the case of the strong force, which is mediated by the chromodynamic field, which classically is kind of similar, also have field lines like this, Gauss's law, the properties of the vacuum. This, by the way, is a photograph of the vacuum, a movie taken by calculations, and that is QCD. This is what the vacuum looks like if you measure the fluctuating chromodynamic field. This is the gluons, which are fluctuating here, and they're charged, little permanent dipoles, magnets. And what they do is something that we've seen in physics before. It's called the Meissner effect. In a superconductor, if you try to introduce a magnetic field, not an electric field, the vacuum squeezes that. It doesn't like to have magnetic charge line. So if you have monopoles instead of the quarks and anti-monopoles in a superconductor, the flux is squeezed to a flux tube. In the case of QCD, we believe that it's the electric dual picture, a flux tube of electric flux lines confining not magnetic monopoles, but electrically charged quarks and gluon quarks in this case. Now, the flux tube has a finite area. And now when you go through Gauss's law, of course, the field no longer falls off because the flux just passes through a constant area, and Gauss's law tells you that the field strength doesn't depend on the distance between the quarks. And now when you calculate the energy, as you pull the quarks apart, it's linear in the distance, and it takes an infinite amount of energy to completely separate the quarks. That's confinement. Now, in the real world, you can pop virtual quark-antiquarks out of the vacuum, right? And you get two flux tubes, and you can separate them. But in a world where there were no quarks, and those were just sources, like in this picture, calculated in that as QCD, where you separate heavy quarks or fixed sources, you see the flux tube being developed. And lattice QCD reproduces the real world as well as this phenomena. So we believe in confinement. Quarks have never been seen, so we believe in confinement. We have many analogs of confinement, like the dual superconductor. We have no rigorous proof of confinement, but it's certainly true. Now notice, this is sort of like a fat string. And this is one of the indications that these mesons, these flux tubes that we see in QCD, might have a dual description as strings. And it explains why people trying to construct a phenomenological model of the strong interactions were led to string theory. They were trying to explain the behavior of such mesons, which are like strings. Now, historically, it was very interesting to see the impact of QCD on my colleagues. There were a bunch of people, some of whom are listed here, who I regard as the smart physicists, who immediately accepted this. I mean, this is a deep puzzle. And suddenly, boom, puzzle is solved, maybe, and you could calculate. People love to calculate. But most people, at this time, it was really interesting. You had the older generation who knew nothing about Yang-Mills theory and renormalization group and operator, all the tools that had been developed, and they largely ignored this. Then you have the younger people who were miseducated by Chu and Landau, who knew nothing about quantum field theory. So there was a lot of inertia in the system, which lasted for over a decade. But you could calculate. So there were immediately calculations. The scaling was only approached logarithmically. A lot of things you could, deviations from scaling, you could calculate, apply it to different processes. Ideas catch fire in physics if they provide opportunities for young physicists to write a lot of papers. and do a lot of interesting calculations. And most important, which unfortunately is somewhat lacking today in my field, make predictions that could be tested immediately or within a few years. There were very important theoretical milestones very rapidly. Ken Wilson, who should have discovered this, but was incredibly biased towards the idea that whatever happens at high energies is irrelevant. What happens at the lattice space is irrelevant. You just care about infrared fixed points, and didn't believe the experiments. Invented, but switched 180 degrees immediately. I've always admired Ken enormously for that. And said, okay, let's calculate. But not calculate the easy things, weak coupling, high energy, but the hard things, the mass of the proton, strong coupling. So he invented lattice gauge theory. And there you could actually see confinement in the totally unphysical regime where you chose the bare coupling at the lattice spacing to be big. And then you saw strings and confinement, and the idea was then to take the continuum limit and see if that's preserved. He gave up, by the way, 2 years later. Since then, lattice gauge theory, as I'll say in a moment, has become an incredibly precise tool which now can calculate the spectrum of hadrons to better than 1%. But Ken was right in a sense because it required roughly, I estimated, a factor of 10 to the 18 in billion times the calculational power that was lacking because of theoretical knowledge and Moore's law. With Naveau, I constructed a theory which, like QCD, developed a dynamical mass gap and dimensional transmutation, made me feel better about that, and it helped solve for quantum dynamics in 2 dimensions where confinement is trivial, but at least you had an example of a theory whose elementary constituents were confined. I had big arguments in Princeton with my very senior colleague, Eugene Wigner. How can you base a theory on particles that don't exist, that you can't produce as asymptotic states? Because Wigner defined an elementary particle as an asymptotic state, something you see far away where no interactions are taking place. But the idea of basing a theory on particles that you could never see was very upsetting to many people. Anyway, the most interesting development was, as usual, experimental. It happened a year later. And another new accelerator at SLAC, which was smashing electrons and positrons together. They produce photons. Photons can produce any charged particle in pairs, electron, positron, or quark, anti-quark. And you can easily, and in QCD, rigorously calculate the ratio of producing quarks to eventually become hadrons to producing electron-positron, which remain electron and positron. That number simply measures the sum of the square of all the charges of all the elementary constituents of that have charge. And QCD made a prediction with 3 quarks, up, down, strange. That's it. Worked very well. But in 1974, there's a conference in Trieste, which I went to, talked about QCD. Bert Richter appeared, just done this experiment at SLAC. He said, look, this is constant, all right, but look at these events. They're not constant. In fact, they're increasing. Scaling is wrong. All these arguments are wrong. QCD is dead. Experimenters love to do that. They have no greater joy than to destroy theoretical ideas. Now, the smart theorists knew that there had to be more quarks. Electroweak theory requires doublets, up, down, strange, charm. The charm quark had to exist. There were many other reasons the charm quark had to exist. It had to be somewhere, the threshold for producing charm had to be somewhere around here. Theorists were very tentative and shy this time because it's 60 years of failure. Nowadays, they're not shy at all, but then they were. And so some of us said, well, maybe you've produced charm. A few months later, they saw undeniable evidence that they produced charm. They saw bound states of charm, anti-charm particles, which were narrow. Why narrow? Because the force between the quarks was weak, because the particles were heavy and they were close together. So these were very narrow resonances. Many of them, they could be explained using non-relativistic quantum mechanics with a reduced strong force. And then the cross-section leveled off as predicted by QCD, and the story continued. It's a way of discovering the bottom quark. All of these fit beautifully with QCD, plus the existence of the neutral vector meson of the electroweak theory. That convinced a lot of people that QCD was on the right track. But, nature is the judge, and the approach of the theory to free field theory, to asymptotic freedom, is logarithmic. So it's not easy to see. This is 16 years later, 1989. This is a prediction of the theory. Those are the experimental points. Looks consistent. 16 years it took to get this far, and that's not much better than a straight line. But experimenters go to higher energy, much better statistics. This is 40 years later, pretty good. These are the deviations from exact scaling. These are jet cross sections. This is the latest one I could find, which was 50 years later. And now the precision is approaching 0.1%. And most of what happens at the LHC, where there are literally billions of events every nanosecond in these collisions, are these fascinating or boring, depending how you look at it, QCD events, where the theory has gotten so good, much better than the simplest theory we used at the beginning, as well as the experiments, that there are literally hundreds and hundreds of high precision tests of the theory. But what I really wanted to do, as soon as possible, was to calculate the spectrum of the particles around in the universe. All those particles that were being discovered should be able to calculate their spectrum at the very least. But there you really need to control this complicated vacuum. And the only way we really have that a priori, with no assumptions in principle, is lattice QCD. And that has reached a new level of maturity, but it took 40 years or more due to theoretical ingenuity. That's a factor of 1 billion new algorithms, new understanding, finite volume effects, control of light quark, et cetera, and Moore's law, another factor of 1 billion. But now we can calculate the spectrum of hadrons, heavy hadrons, the ones that were being discovered at Berkeley at the time, to better than 1%. You can even calculate the mass difference between the neutron and the proton, which is about 1 part in 1,000. And it has the right sign and the right magnitude to about 1%. It's very important, as you know, that the neutron is heavier than the proton. Otherwise, protons would decay and we wouldn't be here. That's a hard calculation. It's not just electromagnetism would give the opposite result, or the quark masses. It's all of QCD, and it can be now done. Theory, in addition, has greatly improved its perturbative ability. This is the beta function that we calculated, gives rise to asymptotic freedom. It's now calculated not just to 3 terms here, but to 5 terms. There's a whole industry of calculating perturbative QCD. Not just the leading order, which we calculated, but the next to leading order, next to next, next to next to next. All of this is needed for precision tests of QCD, but more importantly for the experimenters to calculate the background to discover the Higgs, for example. If you looked at the plots that discovered the Higgs, what you see is a curve which goes down, a little bump. Now, how are you sure? You have to understand the background enormously precisely. For that, you need to calculate in QCD up to 3 or 4 loops. Very hard. Literally hundreds of thousands of Feynman diagrams. So theorists have studied the nature of perturbation theory in QCD and discovered unbelievably rich, fascinating mathematical structures, which hint at something very deep, but nobody's figured out what that is. But the structures are beautiful and unbelievably powerful, so they can now do calculations which were unimaginable 20 years ago. Okay, now I want to give adequate praise to QCD, which I claim is the most perfect theory we have of matter because of 3 things. One, it really is a quantum field theory where there are no infinities. All these problems that the pioneers of quantum field theory and quantum mechanics were worried about are really not present. Second, it's the first time we've had a physical theory with no adjustable parameters. It's a bit of a stretch, but I'll explain it. And finally, it's the first theory we've had with no indication within the theory any disaster or new physics required if you go to shorter and shorter distances or higher and higher energies. So first of all, QCD really has no ultraviolet divergences. So there's this bare coupling you have to introduce to define the theory. The coupling you measure at some fixed short distance. Because of asymptotic freedom, that vanishes. It doesn't blow up. It's not an infinity, it's 0. Now, of course, if you divide something finite by 0, you get infinity, but you don't have to divide a number by 0. Lattice QCD, which is the answer to some problem. This is the partition function, the exponential of the vacuum energy, if you want. The path integral. On a lattice, it's a finite dimensional integral. It's the answer. In the end, you need to take the lattice space into 0, get an infinite dimensional integral in a finite volume. The coupling that occurs here is the coupling that characterizes the theory at short distances. But it vanishes when A goes to 0. It's not infinite. To take the continuum limit, calculate physical quantities, you simply let the coupling go to 0 logarithmically. According to the theory, physical quantities remain finite. That's how you calculate the spectrum of hadrons. Infinities. Now we come to no, no, everything's calculable. So recently I went back and read a beautiful article by Feynman, Solvay Conference, 1961, about 10 years after the triumphs of QED. It was summarized in the present status of quantum electrodynamics, surveyed the experiments, everything worked, great. But Feynman was interested in more. He wondered, could we, QED, if you ignore everything else, has two parameters, the electron mass and the fine structure constant. He wasn't satisfied with a theory that had these arbitrary numbers. So he'd like to calculate the electron mass and calculate the fine structure constant. So he said, let's consider pure QED with only zero mass electrons. Could we produce a finite electron mass? Now, there are two reasons why you might have thought you couldn't. One is a symmetry, a chiral symmetry that happens if the electron was massless. But Feynman had read Nambu, who understood spontaneous symmetry breaking, and knew that that symmetry could be spontaneously broken, and you could produce an electron mass. His problem was that of scale invariance. He said, the system is invariant to a change of scale. So there's no parameter to determine a length or an inverse length like the electron mass. An electron with a mass involves such a length. Therefore, he concluded, I am not certain. Feynman was always careful. But it appears to me impossible to generate a specific length from no scale whatsoever. His conclusion was, okay, QED is not a perfect theory. Can't calculate the fine structure constant, this dimensional number, can't generate a mass from nothing. What he didn't realize, of course, or at least he didn't realize, that he should have realized, quantum effects break scale invariance and can produce a physical mass scale and then can determine the coupling at the scale. And that's what QCD does. So in that sense, QCD, if you made the quarks massless or ignore the quarks, has no adjustable parameters. There is a mass scale. It's got to come from somewhere, but it comes from somewhere. And once you decide to use that mass scale, like the kilogram in Paris or the mass of the proton, you're done. Furthermore, you've determined the coupling at that scale. This is called dimensional transmutation. To put in mathematics, to define the theory, we actually have to introduce a scale, the lattice scale, say. Our coupling is defined at that scale. There's a function you can calculate, as we did, that tells you how that coupling varies as you vary the scale. Physical quantities can't depend on this arbitrary scale you've put in. Therefore, any physical quantity depends on the scale and the coupling in this way, solving the equation. Asymptotically free theories for weak coupling, this is clearly a non-perturbative effect. That's obvious. I mean, you're not going to produce a mass if you don't have any other scale unless except non-perturbatively. By the way, if you take a theory which isn't asymptotically free, instead of getting e to the minus 1 over g squared, you get e to the plus 1 over g squared, which is absurd. The weaker the coupling, the bigger the... That's absurd. In fact, an indication that theories like QED don't exist. Something that hasn't yet been proved, but has been proved for other non-asymptotically free theories like 5-4 theory. Which means, in the end, that a physical quantity depends on some mass physical mass scale that's determined, say the proton or the pion, whatever, choose something. Once you've chosen that as your standard kilogram or whatever, all physical quantities don't depend on anything. They're calculable numbers. So in the case of the proton, for example, the proton, neglecting the quark masses, which doesn't change much, I like to tell people, is confined energy. So when you gain a kilogram, as some of us have done in Natal by overeating, wonderful food, we've gained a kilogram of confined energy. The quarks are massless, gluons are massless, so the energy equals mc squared of the proton is just these massless quarks and gluons rattling around in a space whose size is determined by when the coupling gets strong enough to confine them. Once you've determined that mass scale, decided which particle you're going to use as your mass scale, that determines the coupling. And all in that unit of mass, all mass ratios, other particles are calculable. In that calculation I showed you, the mass scale of the hadrons, you choose, well, actually, the real world, the quarks have little masses, so there's some dependence. Choose one of them, everything else is calculable number. There are no adjustable parameters, except, of course, for, the number of colors. Who told you they were 3? Why are they 3? Well, who told you what the masses of the quarks were? They're these small masses, which we know doesn't come from strong interactions. But inherently, this is a theory which has no adjustable parameters. From the point of view of impact on physics, however, the fact that the theory shows no place where it breaks down is incredibly important. No new physics at high energies. High energies, interaction gets weaker and weaker. Perturbation theory becomes more and more exact. Well, that's nice for theorists, but essential for cosmologists. So this period of the 70s, astrophysicists, cosmologists, having discovered the CMB, wanted to probe backward into the history of the universe, to the era where nuclei were going to be interacting. And the early universe seemed scary. So the fact that the theory at high energies became simpler meant high temperatures means high energy, high average energy of the particles. High density means high chemical potential or high average energy, the Fermi sea. Go back to the early universe, nuclear physics becomes simpler, it becomes quark physics. You could use perturbation theory. Instead of a hadron hell, you have quark soup. Not only that, you have interesting phenomena which you might look for. For example, if you heat up nuclei, energy goes up, interactions become weaker. At some point, this confinement, because of strong forces, stops. You get a transition from confined nuclei to some kind of quark-gluon plasma. That really allowed cosmologists, astrophysicists, not to worry. The rest of that and the rest of the standard model, which is also weakly coupled, allowed them not to worry about particle physics at all. Maybe they're interesting phase transitions, which we can maybe have astrophysical implications, but we can go all the way back to the Planck time, as they're now doing. It also suggests an experimental program of probing the structure of nuclear matter or quark matter, gluon matter, as a function of density and temperature. You can create high temperatures in the laboratory by smashing nuclei together, as has been done, to see indications of the deconfinement of hadrons to quarks and gluons. And that is a whole enormous experimental program doing that. Or trying to apply these ideas to neutron stars where the nuclear or maybe quark density is very high. Fundamental physics, it allowed one to extrapolate. Things get simpler. The other forces increase, like electromagnetism, and immediately after the completion of the standard model, people extrapolated the forces to high energies. Now, there could be other things, who knows, but if you just take what we know and extrapolate, remarkable fact is that the forces become kind of equal. Things increase logarithmically at the beginning at very high energies. And this is this clue that the forces unify, the content of matter, the various multiplets of the gauge groups that dictate these forces also fit together as if they come from a unified force. And the fact that this happens where gravity, which is the weakest force in nature and low energies, but increases quadratically with energy. The charge of gravity is energy, mass, has been the most important clue for those of us who are looking to unify all the forces and understand or include quantum gravity. It's led to, for example, string theory. Finally, I just want to remark on one of the things I think is quite remarkable about QCD, which kind of answers one of the large number problems posed by Dirac. Dirac observed there are a lot of large numbers in the universe, which nobody can understand. The Planck mass, this enormous mass, which is constructed out of the fundamental dimensionful parameters in nature, Newton's constant h bar c, is very small. And he said, nobody can calculate 10 to the minus 19. He identified a lot of other large or small numbers, and he didn't invoke anthropic arguments. This number is highly anthropic. If it was not 10 to the minus 19, but 10 to the minus 3, we wouldn't be here. 1,000 protons would form a black hole. Gravity is only weak by a factor of 10 to the minus 40 in the atom compared to electromagnetism because of this number being so small. Dirac said there are other large numbers, like the radius of the universe in atomic units. And he said they're all related, and some of them are time dependent, so some of the fundamental constants of nature should be time dependent. And we've ruled that out more or less because they're permanent nuclear reactors that have been around for about a billion years. Can conclude that, say, the fine structure constant hasn't changed by much over a billion years. But QCD can calculate that ratio with reasonable accuracy. It's very simple. This is asymptotic freedom. This is the unification scale. Assume at the unification scale, the strength of the coupling is, the order of the fine structure constant or bigger, what we know from experiment. You might ask, okay, that's the Planck mass. Where's the proton mass? Well, you follow the coupling down till it gets strong enough to confine the quarks. That defines a scale. And since it's logarithmic, that scale goes like e to the minus something over g squared. So you've turned the logarithm. You've taken the log of this big number, and log of 10 to the minus 19 is something you can calculate. And this is roughly correct. up, maybe not exactly 10 to the minus 19, but 10 to the minus 18 or 20. Conceptually, that's the origin of this small, incredibly small number. It is calculable. So QCD is the first example of a complete theory, nothing missing, no adjustable parameters, no indication where it breaks down, infinite bandwidth. But of course, the real world is more complicated, luckily, more interesting. Even within QCD, there are these parameters we can't calculate, like the number of colors, the masses, the mixing, and of course, the other forces. I'm going to end with just a remark or two about string theory. That, in the end, is the most important lesson of QCD, I think. So we saw this flux tube looks like a fat string. String theory has a thin string connecting two quarks or ends. These theories were developed at the same time, roughly. We really believe that they're the same thing in some sense. Now, string theory, as such, once you have open strings, you can close them. And in string theory, it was discovered that closed strings behave just like the quanta of gravity. They mediate a force which looks like Einstein's gravity. I'm going to skip this. And we now understand that very precisely in a very simple, beautiful example that was the subject of Pedro's talk yesterday. This duality between string theory, open strings and closed strings, ordinary non-abelian gauge theory is supersymmetric even in flat Minkowski space with rigid geometry, no dynamical space-time. And strings in anti-de Sitter space, which is like putting gravity space-time in a box. And these are the same the same physics described in two completely different fashions. This is ordinary quantum mechanics. What's essential for this simple connection is the conformal invariance of this theory, but it's a close cousin of QCD. It can be deformed continuously to QCD. And closed strings in a curved space-time, which large distances and here large number of colors, here weak Newton's constant, looks like Einstein's general relativity. Except this theory is quantum, as is this. This is a definition of a theory of quantum gravity, which looked like Einstein's theory with quantum corrections, and is consistent and allows us to explore emergent space-time, properties of black holes, lots of interesting questions. From the point of view of QCD, the hope is that we could solve that theory. Pedro described how you solve such theories, and then use that theory for a large number of colors and using information from the string theory side to deform to real QCD. So that's one of the well-defined goals of actually solving analytically or approaching analytic control of QCD, not just at short distances, but large distances. So what's the future of QCD? This theory, like Maxwell's theory, is going to be around for centuries and studied for centuries. Lots of interesting physics. It's much richer and more interesting than Maxwell's theory, which is still being studied some places. There will be lots of development of perturbative physics, amplitudes. There'll be increased numerical techniques, already pretty powerful, but they're not powerful enough to tell us about non-static properties. It's the sign problem in numerical simulation. But now we have perhaps new computers, quantum computers, other techniques, which might allow us to approach most of the interesting physics which can't be approached at the moment. And then there's experiment, which goes on. There's LHC, which does these precision tests. There's LHCb, which has discovered dozens of new hadronic states. Some of them not just made out of 3 quarks or 2 quark or quark antiquark, sometimes 4 quarks or 5 quarks, a fascinating spectrum of so-called exotic hadrons. There are these experiments which probe the high temperature, high density behavior of quark matter, may be relevant for neutron stars when you smash nuclei together. And then there's the modern version of the SLAC experiment that started it all at a new accelerator that's being built at Brookhaven, the electron-ion collider, where you actually scatter electrons off high energy protons or nuclei and probe the structure, again, of protons, but at higher energies, more precise, and of nuclei. So let me just summarize. Now, I've always been impressed by this summary of physics by Feynman, who said, imagine some cataclysm. All scientific knowledge is destroyed. Only one sentence passed on to the next generation of creatures, either cockroaches or ChatGPT, who knows. What statement would contain the most information in the fewest of words? And he did a marvelous job. All things are made of atoms, little particles that move around in perpetual motion, attracting each other when they are a little distance apart, but repelling if you squeeze them together even more. Get a lot of physics from that one sentence if you're a smart cockroach. Well, it's hard to do that for what we know now. Let's say from the Standard Model. This is a one slide lessons from the Standard Model. What have we learned the last 50 years? Matter's made out of charged spin 1/2 fermions, forces described by quantum gauge field theory, which exists in 3 phases: electromagnetism, long range, Coulomb phase, unbroken symmetry, the weak interactions, screened or Higgsed by an unnatural sector, which still has mysteries, and the strong interaction where the the symmetry is unbroken and the charges are confined. What have we learned after 50 years from QCD? Well, the most important thing, of course, we've learned is that QCD is a theory of the nuclear force. Second thing I think we've learned is that it is possible to have a theory which at the very least determines all masses and all couplings and has no adjustable parameters. So that's an achievement. It's not the real world, but it seemed to me to be the demand we'd make from a better theory. All theories are tentative to be replaced, but the least we should expect from another theory is that it determines all masses and couplings. And finally, I think the most important thing we learned is that gauge theory, these gauge theories, which provide the Standard Model, are the same framework. They're really the same as string theories. So the real hero behind QCD and the rest of the Standard Model are gauge theories, non-abelian gauge theories. They are the explanation of QCD, of the Standard Model, but they're also really dual descriptions of some physics, which is also described by string theory, which, as we know, describes space-time, dynamical space-time, quantum gravity. So with that, finally, I end. but not the end of QCD. Thank you.